Okay, so find the slide, and we'll start with Autumn. You always get started first. That's okay. I think she's okay with that. So how I would like to work this is a few things, and I'll ask you directed questions. And what's that? I have a slide that's like the second or third slide in part 3. It's a slide, and it says concentration of solutions. It says parts per 100. It says 20 grams of NaCl. Good, 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 good. You find it too? What page is it on? On page 2. On page 2. Okay. Yep. Okay. So I think, Autumn, my first question is, help me out with molarity. What's molarity? It's blank over blank. Moles over liters. Perfect. So when you're working this sort of problem, it's good to kind of know what your target is. We're supposed to get to moles of, in this case, Hg2+ per liter. Directed question then, Natalie, what element is Hg?
Mercury.
It is mercury. Mercury plus 2 cation. Very good. It's plus 2, and so I'll stick with you one more question, Natalie. So plus 2, did it lose 2 electrons or gain 2 electrons? It lost 2 electrons. Yep, it lost 2 electrons plus become a plus 2 cation. Moles per liter is where we're after. So now, Billy, did you find this page? Did you find it? Okay, can you tell me on that page, I feel like a lawyer, can you tell me on that page, what's parts per billion in terms of, at the end of parts per billion, what does that mean in terms of grams per liter? So it's the second problem, and 2 parts per billion is converted to what? Like at the end, like, right, yeah. So 6, yeah, so what, bless you. What I was trying, my point was going to be is 16 parts per billion is the same thing as 16 micrograms per 1 liter. Does that make sense? According to this. According to the pattern, 16 micrograms. Because parts per billion is the same thing as micrograms per liter. Are we good with that? Mm-hmm. Okay. Okay. So, we're on our way then. All right. So, on to you, Taylor. So, how would you fill this in? Blank micrograms is equal to blank grams. What numbers would I put there? The micro, yeah, what does it mean? And I don't know if you want this hint because you go either way, but what if I put a 1 gram there? 1 gram is equal to how many micro? Yeah, you have to remember what the prefix micro. Your options are 10 to the negative 6 is, is it? Maybe it is. Oh my gosh. Yes, you're right. I was thinking, very good. Okay. So here, this would be 1 times 10 to the 6th micrograms is equal to 1 gram. Does that, you buy that? Okay, so you came up with that. Very good. What's that? I don't know what I'm thinking, but anyway. Okay, good job. Okay, so units have canceled of micrograms. Now, Glenna, find mercury on the periodic table and tell me what its molar mass is. No, I'm getting a bigger number. Did you say 100?
What number?
Oh, the decimal number. It's the decimal number. Okay, thank you. 200.59. Okay, and we said that that's what I call the decimal number for mercury, and it serves double duty. It is how much a mercury atom weighs, but it's also the grams per mole. It's what we call the molar mass of mercury. Oh, a molar mass of mercury. Okay, so we've kind of come back to you now, Autumn. Can you use the molar mass as a third term here to have grams cancel from the second term and be left with moles in the numerator? So use this. So that's 200.59 grams per mole or per 1 mole.
So 1 mole.
Mm-hmm.
And then 200.
Yep. She said 1 mole on the top and 200.59 grams on the bottom. Oh, Natalie, can you type that out? That's a hard one. Can you do it? Luck of the draw. So to work this problem number-wise, you're going to take 16 and you're going to divide it by 1 times 10 to the 6th, and also you're going to divide it by 200.59.
What is... Okay, so...
You can multiply the bottom two before you divide it.
Yeah, you can multiply the bottom 2 before you divide it, if that helps. Do you want to borrow this calculator? Would it make a difference? Is that your phone or is it the same day?
Yeah, let's see.
Yeah. And I like the points, so I actually yeah, the calculators are powerful this idea.
How do you do this? This one?
Oh, I told you the wrong one. It's this one. Okay. It's the common one.
Okay.
I get for seeing upside down. Then you got it.
What about the 1 times 10 to the 6? It's 1 and then the E and then 10 to the 6, right?
Yeah, 1 and E and then just 6.
Oh.
Yep. You don't do that.
7.976 to the -8.
Cool. So give me just two decimals, like 7 point what?
97.
7.97. So it'll be, wow, 7.97. So that raises the 9 up to a 10. So at 8.0, does that sound right? 8.0 times 10 to the what?
-8.
-8. Very good. And then, so Billy, you've been following along. What will my units be? Not liters per mole, moles per liter. Yep. You guys answered Billy's question. Do you buy this, Billy? Moles per liter? Because my micrograms cancel, my grams cancel, and I have moles in the top and liters in the bottom. It's true. Oh. Well, since they answered your question, you have to, that's it, that's the answer. So you have to help me out with the next one, Lily. All right, I'm gonna set it up this way. We have two solutions, 1.5 molar and 0.15 molar, okay, it's NaCl, and they're asking for how many moles are present in 500 milliliters. So I'm going to draw, this is my first solution, which is 1.5 molar. This is my second solution that is, better make some liquid here, which is 0.15 molar. In each case, I have 500 milliliters. And I'm going to show you where you almost don't have to use a calculator for this. So, Billy, here's the question. When I see the M for molar, what does molar mean? M, what does that mean? What? Oh, thank you. Go ahead. What does molar mean? Like it means a ratio, blank over blank. Moles per liter. Yep, exactly. Moles per liter. Okay, so I'll go back to you, Taylor. 500 milliliters, how much is that relative to a liter? Right, if a milliliter is 1,000 liters, so how much is 500 milliliters? So you told me 1 liter is equal to 1,000 milliliters. So if you only have 500 milliliters, how much of a liter do you have? If I took 500 plus 500, I'd get 1,000. So 500 is what fraction of a liter is what I was after. Half. Yep, exactly. Do we all buy that? A half a liter? This is kind of like we're just dealing with buying milk, half a liter. So sometimes I'll do it this way then. Based on kind of on what Billy said, I'll throw this at you, Glenna. So 1.5 molar, what does that mean? Blank moles per 1 liter. 1.5 molar. Because Billy told me this is what, and he's right, this is what molarity means. So 1.5 molar means moles over 1 liter. Would you buy it if I said 1.5 moles over 1 liter?
Well, yeah, that's what I said. Yes.
No, I didn't, but this is what 1.5.
I don't know,
Yeah. No, it's not. I have 1.5 M is 1.5 moles over 1 liter. Okay, so then do an analogous thing, Glenna, over here. 0.15 molar. What does that mean? 0.15 moles over 1 liter.
Yeah.
Right. Thank you. That I know it wasn't a very good guided question.
Well, I guess simple, but I think I'm thinking.
You're overthinking it. I get that a lot in chemistry. You're like 7 steps beyond where I'm at. So just eyeballing it then, Autumn, what do you think? If this is 1.5 moles per liter, and we only have a half a liter, how many moles do we have? 0.75. Are we good with that? Does that make sense? Yeah. That's the answer. How many moles of solute? So bottom line, we have 0.75 moles of NaCl here. Does that make sense? Because the way I got that, and the way she got that, was we know that because the molarity, it's like the concentration, is for every 1 liter we have 1.5 moles. And we only have a half a liter, not a full liter.
Oh, so 1.5 divided by 2.
Yes. And so, Natalie, what do you think over here? Let's finish this off then. Over here for this guy right here. We decided, or between all of us, we're going with 0.15 moles per 1 liter. Well, how many moles would there be in a half liter?
0.075.
0.075. Will we buy that? That's it. Totally it. All our scribblings.
So you don't have to do the molar mass, you know, or anything.
Do not have to do the molar mass at all, because we're just sticking with moles, we're not going. You have to use the molar mass if you had grams involved. Now, the way we did this one, the way we did B, is what we're gonna do with C and D. So are you ready? Okay. So C looks like this. I have a picture here. If you read it a few times, I'll let you read it, and I'm gonna draw my picture. Here's my first solution, and notice I'm putting 0.50 moles in it, and I've got a total volume of 250 milliliters. I am a firm believer in pictures sometimes, drawing or doing chemistry problems. It's funny because on here, for my, I'll call this solution A and I'll call this solution B, I did this line and then I had to scratch it out because actually they tell us this is 200 milliliters and I wanted to show it that B was less than A. So I had to scratch it out twice. So, and then over here, we're dosing it with 0.60 moles, okay? And in both cases, we're dealing with the solute. The thing we're adding is NaCl. Which solution is more concentrated? Why? See, he gets it. And he's right, because I didn't have any calculations here. B, there's more solute, okay, which, you know, can make it more concentrated, and there's less water, which makes it more concentrated. So this is more concentrated. Yep. Thank you. Let's go back. Any questions about that? Wish they were all like that. I have another one last one. And it looks like this. I'll draw my little picture. When you read it a few times, what I do with a problem like this, I say want, what our target is. We want 1.0 liter of 2.0, big M means molar, CuSO4. So then down, okay. So I'm gonna actually not draw the picture yet. So help me out, Taylor. What I usually do in a problem like this is I do the one that Glenna had. Ooh. Okay, uh-oh. We got the ant thing going on here. So what I do is what we had Glenna do, I call it unpacking. Can you tell me, when we're talking about 2.0 M CuSO4, what does that mean in a ratio? Like a dump over... Yep, 2 moles, 2.0 moles. That's all I was after. 2.0 moles of CuSO4 over 1 liter of solution. Perfect. That's what our target is. And so here I drew a little picture. Okay, I drew, this is 1.0 liters, or 1 liter. And then in my figure, so Glenna, can you help me out? 1 liter is equal to how many milliliters? 1,000, thank you. You talk fast. No, you're fine. 1 liter is equal to 1,000 milliliters, perfect. Okay. And then the problem statement says that we are going to go ahead and dose this with 40.0 grams of CuSO4. That's from the problem. And the question is this 2 molar? Now, this is one where we do have to do the molar mass, because basically, you know that you want 2 moles per liter, and in our problem, I have 1 liter. So to me, the question here is 40.0 grams, is that 2 moles? Does that make sense? Is it 2 moles? And if it is 2 moles, we did it. If it's not 2 moles, then we can answer this question which wasn't done. So the thing is, we need to know how many grams you got to weigh out to get a mole of the CuSO4. So here's where we need grams per mole for CuSO4. And the way we do that is the periodic table. So, Autumn, can you help me out? What is the decimal number? We have to add up all these decimal numbers. What's the decimal number for copper?
63.546.
Very good. And decimal number for sulfur?
32.6.
Awesome. How about the decimal number for oxygen? I'm going to multiply it by 4.
16 times 4.
16 times 4. Perfect.
54.
Awesome. And and I won't pick on Natalie because we picked on you a lot with her. But anyway, we'll pick on you later. So do you have a number for that? Happen to have a number for that? All of those added together? But I am going to pick on you with the answer. So she's going to tell us 159.606. That's fine. And that's grams in 1 mole. All right. All right, Natalie. So to get 1 mole, that's the mass you need to weigh out. Question is, did we weigh out 2 moles when we weighed out 40.0? If this is the maximum one. It's 159.606 grams in 1 mole. Is 40 grams 2 moles? No. No. Very good. The answer is no. How would we get 2 moles from this number? Double it. Yes, ma'am. So if we want to do this right, we just take 2 times 159.606, add it to our 1 liter, and we have 2 moles. And then here's my favorite number. 40 is my favorite number, as we established last time we met.
Why is 40 your favorite number?
Because it's molar mass of sodium hydroxide that I come up with. No, unless we use a different. Duh! Right. Okay, so these were the, the ones you can just kind of look at. Okay, on to part 4. Whew! My goodness gracious. Now this one, the copier only does what you ask it to do. So I'll leave you to decide what I asked the copier to do. I don't know. In my defense, mine. All right. Way back when we started this class, we talked about compounds, and compounds are where atoms join together to make a repeating unit. Compounds can either be ionic compounds or molecular compounds. So we're going to kind of focus on ionic compounds. So sodium chloride, what do we know about sodium chloride, Billy? NaCl. It's salt, it's table salt, yep. So if you were to try to dissolve table salt, this is what it would look like. You can kind of see, and this cannot be drawn to scale. I can't believe it. These are our water, these Mickey Mouses, water molecules. They're going to attack our NaCl. Okay? Now, can you, Taylor, kind of describe to me what is that S-looking thing with the symbol negative? What is that? Partially negative. Perfect. So we kind of see where kind of the oxygens in our Mickey Mouse, because we have oxygen and 2 hydrogens, are partially negative, is kind of absconding or lining up with our Na plus cations in our table salt. Because table salt is Na plus and Cl minus. That's table salt. So I think you already have it here then. I don't have a question here yet for you, Glennon. But so here our partially positive hydrogens for our water molecule are kind of running away with our chloride ions. I think we we talked about this before, 97% is the number up there. 97% of the water on our planet is seawater, salt water. And there's all sorts of neat, innovative ways to try to refine that salt water so we can use it to drink. But if you're like on a life raft and you're in the middle of the ocean, I've seen this like on TV, don't drink the water because it'll do all sorts of nasty things. So since water is polar, the partially negative charges on the oxygen carry away the positive cation, and the partially positive charges carry away the negative chloride ion. The word is dissolution. This results in the dissolution of salt. Dissolution. In other words, dissolving of. Oops. I could see on Taylor's expression like, oh, there goes the word.
Well, it kept going way from the back and going way from the back.
Yeah. I'm trying to emphasize it, but then I went too far. Okay. We could like use a chemical equation. We all love chemical equations. So here is the question now. Now to you, Glenna. So what does the AQ stand for? Remember? I think it's Spanish almost. Maybe not. Aqueous. AQ stands for aqueous. So anytime you see an AQ, think water. Think dissolved in water. So this is actually just showing the dissolving process. Solid NaCl dissolves in water to give you Na plus AQ plus Cl minus AQ. So here's one for you, Glenna. Looking at the, well, I'll put it this way. What if it's not NaCl? What if it's, we have a barium cation? What charge is barium? Just looking at the periodic table. Positive, yep, positive 2, positive 2, perfect. What charge is, what charge is nitrogen while you're there? -3, perfect. So that's the sort of thing you're probably going to want to kind of remember as we're doing these. I think we talked a little bit about polyatomic ions. The word I have here is dissolve. To me, dissolution, dissolve, they mean the same thing, right? Dissolution and dissolve mean the same thing. Actually, there's even more words in science that we use for, sometimes we talk about ionization, same thing. There's another word, I can't think of it. So here we have, do you guys have to write this down? Just here's a formula where I'll read it off to you. Na2SO4, S stands for solid. We have the arrow, goes to form. Over the arrow, we have H2O. Then we have 2 Na plus, AQ, plus SO4 2 minus, AQ. So, Autumn, do you remember the name of SO4 2 minus? S. And it ends in 8. Oh, sulfate. Yeah, SO4 2 minus is sulfate. Yes. So this is just showing the dissolving. But do you see where we talk about balancing equations? Where the reason we have to put a 2 in front of the Na plus is because we have a subscript 2 there. And the SO4 2 minus stays together as a unit. It's a polyatomic ion. All right. So you're going to have to refer to this in a minute to do the next what if question. But not so surprising, not everything dissolves in water. Like sodium chloride, it dissolves into water. But what happens if you keep adding salt into water? Will there come a time when it will dissolve? Yes. If I were to take chalk, we have a chalkboard in here. If I were to take chalk, does chalk dissolve in water? No. So these are what we call general solubility rules. What's that?
But I always think of like sugar and milk, like when you put sugar in your cereal.
Sugar and milk, yeah. Yeah, and it doesn't, you find sugar sludge at the bottom if you add too much sugar. Yeah. Is that what you mean?
Yeah.
Yeah.
Like when you put it on the cereal, because the cereal's too sugary already.
True, yeah. So the first line, sodium, potassium, and ammonium are all soluble, and there are no exceptions. Nitrates. I'll put nitrate, I'll put NO3 minus. That's what you deal with nitrates. NO3 minus. Notice that they are all soluble and there are no exceptions. I guess I didn't know that. These are called solubility rules. These are solubility rules. Chlorides. Who would we last leave on? Are you ready for? Oh yeah. So chlorides. Can you tell me, Nat, what charge chlorine forms? Look at the periodic table. It does, a -1. So chlorides would be that with a -1. They're mostly soluble. Now here we have two exceptions. If we have silver chloride or mercury 1 chloride, they are going to be what we say precipitate out. Sulfates. Billy, Tashi 1, what's the formula for sulfate? It is SO4, very good. SO4 2 minus. Sulfates, they're mostly soluble. Gosh, this thing just keeps having a mind of its own. Mostly soluble. There are a few exceptions, and the exceptions, I hate the exception. I'm gonna put a frowny face with the exceptions. You're like, really? It just makes life difficult. So in other words, if you are dealing with strontium sulfate, barium sulfate, or lead sulfate, it's gonna precipitate out. It's gonna be like when you pour sugar, too much sugar on your cereal. It's gonna have a sludge at the bottom. Carbonates. So what do you think, Taylor? Do you remember the formula for carbonate? It's not 4. Yep, CO3. Yep, CO3 2 minus. That's carbonate. Yep. And carbonates are mostly insoluble. Oh, dang. I mentioned chalk. Chalk is calcium carbonate. Right. The shells of sea animals they have a lot of calcium carbonate in them. Mostly insoluble, which means that they don't dissolve. Okay, so Glenna, do you remember the formula for hydroxide? Okay, we'll give you a different one. The formula for hydroxide is that. Okay, Glenna, though, for sulfur, what charge does it form? She's got it in her. Negative. -2. Yep, -2 or 2 minus. Perfect. So that's sulfide and that's hydroxide. So if you see these in your formula, they're mostly insoluble, but things that are exceptions are that if they are combining with group 1 metals. So Autumn, help me out. When group 1 metals, what are group 1 metals?
Like hydrogen. Now lithium?
Yeah, starting with lithium, sodium. Yep, these are group 1. Cesium, yep, group 1. Very good. Perfect.
So the formula is directly related to whether it's soluble or not?
No, I wish it were that easy.
Or
What this is saying,
or this is something you have to memorize.
Just something you have to memorize. In fact, we just covered this in Gen Chem 2, and students hate this, and so do I. So, yeah, I should say it this one. Oh my gosh, I was like, that's my sound.
I'm already calling you.
You're fine. I'm just glad it's not me. So, yeah. What's that?
When you're old, you can't hear it. I think that's what it is about the brain.
Okay, so here we go, your turn. And I think we're back to Billy. So remember on your test, for your final exam, you know, I see some of you guys have these. You know, you can take this to your final exam. You can take your textbook if you have a copy of the textbook. You can take your calculator, your favorite calculator, to the final exam. So I know it's going to be important, but anyway. Okay? So, Billy, ammonium nitrate. I haven't done these. Look at ammonium nitrate. So find a solubility rule where you think, see, I see nitrate. Not gonna help you, Billy. So I see nitrate. I'm thinking soluble. Okay, the next one. What do you think, Taylor? Sodium sulfate. Soluble or insoluble?
Sodium, all soluble, sulfates, mostly all.
Mostly all? So if it's mostly all, you look at for sulfates, you look under the third column for exceptions. So, and to me, the fact I don't see sodium there means, what would you gather? I don't have my things still in, but so for that,
mostly soluble, and if we're talking about sodium sulfate, the fact that there's no sodium here, I'm like, okay, so I'm I'd say soluble, or mostly soluble, I'd say soluble.
okay, Glenna. So, not Cinnabon. I know, that's what I thought, Cinnabon. I'm like, mercury too sulfur? So Glenna. You're saying soluble, mercury 2 sulfide.
Because mercury is mostly soluble.
Yeah. I'm thinking. Wait, is it the last? So what did the last one say? What was this box here for hydroxide and sulfides?
Oh, okay. But is there no difference?
I'm thinking the fact that mercury.
See, I think the sulfide. No wonder they make this.
Yeah, I know, right? Just Google it.
Well, correct. For some reason, couldn't straight to the internet. See, to me, so yeah, it's not useful.
Google it ahead of time.
The first thing you look at is these. You don't look at
See, deception.
I went to Mercury. Yeah, but don't look at look at sulfide. Oh, yep, I got it. Yeah, so look at sulfide first, and then no mercury 2
Yeah, I think we're on the same page. Yeah, let's look at the first column first, and then hopefully there's something there. So we're going with insoluble.
Mostly insoluble or just?
I think I'm gonna put insoluble. When it says mostly, they're talking about like with different salts. They're not talking about whether it's mostly insoluble.
So even though it's a mercury there, you decided that that's the exception, so it's not.
Yeah,
insoluble.
but you go here, like we don't do this first. We do this first, and we have a soluble.
And then you just go with that.
Yes. Yeah, and because there's no exception, there's no mercury here. So what do you think about that last one, aluminum hydroxide? So we're up to
Insoluble. Wait. Yes.
I would tend to agree, insoluble. Any questions? Yeah, it's funny. Yeah, I will pass along. You can see why they hate that. Yes. Yes. But the solubility of salts can be a big hairy deal, especially if you're talking about, well, we'll talk a little bit about the pollutants. If you have something that's toxic, and it's soluble, you don't want that in your water stream, okay? If it's insoluble, you're like, right. If it's in,
We know those aren't crossed out with pesticides and stuff,
yeah. If it's insoluble, you're like, that's different. But then if it's insoluble, it's probably not going to be practical to be used in as a fertilizer because you need it to be soluble. So anyway, there's a list of sources and ions and solubility consequences. So for instance, fertilizers, nitrates are generally soluble, and then that runoff can be toxic for infants, And I don't mean to be political. I can't help it these days. And actually, the things we're talking about are near and dear to some changes that are going on right now. So. Anyway, okay. Changing subject. So ionic compounds, earlier today we did the whole NaCl breaks apart into Na+ and Cl-. The thing about it is if you can have those pluses and minuses running around in water, they can help create a path for an electrical current to flow. Okay, that's called electrical conductivity. And it makes you want to try this, and I don't have it here to try, but you're going to see 3 photos, you can already see them, where basically we've got a light bulb. Can you see that light bulb there? It's not lit up. The point is it's little tiny right there. It's a non-illuminated light bulb. So the way this works is we have a battery that is trying to send electrical current here, go through the water, and then take another electrode here. Complete a circle. If it completes a circuit, your light bulb lights up. That's about as much as I know about electricity. In pure water, your light bulb will not light up. Okay? It's what we say non-conducting. Non-conducting is the word. Just because I know it. Non-conducting. Okay. Well, here's the deal. Okay, let's say these are sugar cubes. We dissolve sugar in water, and is the light bulb lit up? No, light bulb not lit up. But will sugar dissolve in water? Yeah. It dissolves in water, but it stays in its molecule. It doesn't give pluses and minuses. Well, the last but not least, yay, and the word is conducting there. We're making salt water. Is the light bulb lit up? Yes. And the light bulb's lit up because it has, within this water here, we have pluses and minuses that help complete the circuit. So we can have, our battery does its thing and powers the light bulb.
So if you had Gatorade in there.
Gatorade would, yeah, the electrolytes in Gatorade, yep. I almost, but then I chose not to. They had a your turn question, and it said, well, what about, you hear people that, you're not supposed to use electrical appliances when you're taking a bath? Like, duh, right? No hair dryers sort of thing in the bath? Yeah. Oh my God. But so if that's the case, if your bath water is pure water, no one should ever get shocked. You can use a hair dryer. And the answer to really, if it's pure. The problem is we dove into a little bit in lab. When you guys did your chloride ion test, okay, for your water samples, there's chloride in water. There's all sorts of different things in pure water. So
you probably should not try your hair dryer.
Right. Even though it's not salt water, there are other ions in there. Have you ever heard of hard water, soft water? You have other ions in your water. So it will conduct electricity.
Does water softener and stuff like that affect that?
Yes. Yeah, the water softener will be adding ions to your water. Yep. So the word up here is strong electrolytes. Oh, by the way, and I read this in the appendix that has the answers to your questions. With regard to the hair dryer in your bathtub, it says if you have such an issue, you're supposed to unplug it first remove the hair dryer. So. Okay.
I just watched Murder Mystery.
Don't just.
You should be a
murdered his girlfriend.
I watched like 1,000 Ways to Die and only died because of that. How was she unlucky?
I don't know how that works, but.
Aren't you not supposed to get out of the water? Wait.
I don't think you should have had that haircut.
I think this is assuming that you're not in the bathtub, that you have accidentally dropped without anybody in there, your dryer, so don't reach in and get it. Okay, so we have if something can light up the bulb, the light bulb, if it can allow for a current to pass, we call that a strong electrolyte. There is something called a weak electrolyte, okay, where it only partially gives you ions, and then a non-electrolyte. So sugar was a non-electrolyte. And here's a picture of, this actually is sugar. This is our sugar that dissolves in water to a certain extent. It's a pretty molecule, it's a big molecule. Well, not as big as like other things. So sugar will dissolve in water, but it does not, the word here is dissociate. Did we use that before? Dissociate, dissolve. Okay, same thing. Okay. Well, I think that's where we're gonna have to stop. I think we'll do some booking on, we'll be fine. Because Monday I'm hoping to kind of finish up this chapter, which is this part, and it goes to part 6, so this is just part 4, 4, 5, and 6. We'll just see. See how so have a good weekend. Is there any, is there any homework due?
Not chapter 8 was due Monday.
No, I got chapter 8 homework is due a week from Monday. It's the 16th. But I'm hoping to finish up in lecture. And then your exam is also due the 16th, so that's kind of a pattern. I'm gonna see you at 2.
Are you using your lab room later?
Am I using what?
Your lab room later?
No, it's a little messy, but you make yourself at home. You got something to record?
Yep. Another video.